Hi, AP Calculus students. We are starting section 4.1, antiderivatives. Those are called integrals. It is a new operation, as you saw in the introductory video. It is this elongated S symbol. And this section I think is fun, really. We are simply taking functions and integrating them, finding the antiderivative. So it's just kind of fun working backwards. And it's really nice because you're just kind of chugging along. It's kind of nice when you're just kind of calculating and just doing operations consistently over and over. You get kind of a nice feel for it, I think. And so 4.1 is a great section to start with that. So in this video, I'm just doing notes. We will be doing the examples in class because it's our first day after winter break and we need something to do, right? So we're going to do the examples together, but if you could get these notes down, that would help. So definition, a function f, and this is a capital F, is an antiderivative of small f of x. You know, I should probably put an x on that capital. So let's try that again. Here we go. A function capital F of x is an antiderivative of small f of x on an interval I if, when you take the derivative of the capital F of x, you get the small f of x, right? So what this means is whenever we are integrating a function f to get its antiderivative, capital F of x, we can always check to see if we're right by taking the derivative and seeing if we get the original function back. So it's really kind of nice, it's self-checking. So a differential equation, you've seen these, has derivatives in it. So to solve, that means that you are eliminating the derivatives. You may have to integrate or find the antiderivative once. You may have to do that a couple times. So to solve, you just take the antiderivative to find the f of x or y, right, interchangeable. So if you have been given this differential equation, so they're saying that the differential of y divided by the differential of x, so that's the derivative of y with respect to x, simply written in Leibniz form, which instead of the prime sign, which I do use consistently through this section, and you'll see why. So if you have a derivative that is equal to a function, and they are asking you to solve this differential equation by getting rid of the derivative and just leaving yourself with y, here's what we do first. Notice that what we need to do is this is called the differential of y and the differential of x. And they have to be paired with a function that has a matching variable. In other words, this differential of x, I need with f of x. It has to be next to the function that has that variable in it. So simply, really all we're doing here is if I multiply both sides by dx, the dx's cancel, the differentials of x on the left, and then I have the differential y equals f of x with the differential of x. Another good reason to do this is because now this is the differential of y, and when I integrate on the left, an integral and a derivative are inverse operations and they'll cancel and just leave me with the y. So when you're solving differential equations, you really do want as much as possible the y alone, so that when you integrate and remove that derivative, you just have that y. You don't have to do any algebra after that, okay? So the differential of y equals f of x dx. So let's integrate both sides. Let's do the inverse operation of a derivative, right? And so what happens here then is the antiderivative and the derivative cancel, and I'm left with y. We write the antiderivative of a function as a capital F of x and plus c. Okay, so first of all, notice here that as I said in my introductory video, that the integral symbol and the differential are a pair that go together. And when I actually integrate, these do both eliminate, and I am left with the integral function. Now we have to have a plus C every time. This is so important. They will mark you down on the AP exam if you integrate a function and do not put the plus C. Okay, they will take part of it off. And I also take, if you integrate on a memorization quiz and don't put a plus C, I also take points off. And I'm sorry to do it to you, but it's tough love so that it doesn't happen to you on the exam. This is called a general solution. Y equals this function plus C, some constant. And it's called a general solution because if C is 1, if it's 3, if it's -5, it makes a different function every time. So Y equals capital F of X plus C actually makes a family of functions. We'll see that over here. Okay. So, and by the way, I already said that this is the differential Y differential of X, but I just want to point out, we do have a word also is when you are integrating this function, this is called the integrand. I'm going to write it this way, integrand. That is the function that is being integrated, kind of like under a radical sign, that like a square root sign, cube root, that expression underneath that radical sign is called a radicand. That's what you're taking the radical of. Okay. Number 3, if you have an integrated function plus C of an original function, how do you get a particular solution from the family of solutions? In other words, how do you find C? So this is called a general solution because C can be, anything you want it to be. How, if you have a family of functions, how do you find the one particular function that you're referring to? Here's your answer. You need an initial condition, that's a starting point, that you substitute into Y equals capital F of X plus C to find the C. Okay, so here's our example here. Let's say you have a function F of X equals 2X. We keep using this over and over, right? What is the general solution? Now, I wrote it myself here because we've done this a couple times. So let's just check. If I take the derivative of this function, right, I do get 2x, and the derivative of a constant is 0, right? Notice that this is why we need the plus C when we integrate, because when we take the derivative, it is a 0. So if I give you this function f of x equals 2x, and I ask you, what is the antiderivative? Notice that that would be the function. If you took the derivative of it, you would get 2x back. Well, take a look here. Y equals x squared. When you take the derivative, you will get a 2x back. X squared plus 1. When you take the derivative, you get a 2x back. X squared plus 2, you get a 2x back. So that is why when you are writing an antiderivative, you have to have the plus C. This is a vertical shift, and it creates this family of functions because all of these functions, when you take the derivative, give you the 2x. So how do I get one particular solution from the family? You need an initial condition. You need a point, right? If they say, integrate this function and give this solution, and they give you a 0.00, right? Or a 0.01, right? Then you know which one of these actual graphs or equations to choose, right? The particular solution. So let's go on over here. So if you have y equals x squared plus c, right? That was our integrated function that we got when we integrated f of x equals 2x. If this function has an initial condition of 1, 5, in other words, this point lies on this graph, what is the particular solution? So what we do is, here's our x, here's our y, and we solve for the c. So we have 5 equals 1 squared plus c. Notice that is 5 equals 1 plus some number. Obviously, c equals 4. And so our particular solution, given an initial condition of the 0.15, is y equals x squared plus 4. Super easy. And so it just makes it kind of fun, I think. So a couple things. I suggest looking at page 250. Those are basic integration formulas. All they've done is taking the derivatives you know and reverse them. Okay, the power rule for integration. So this is so cool. So remember when you took the derivative of x to the n, you would bring the exponent out front and multiply it and reduce the exponent by 1. So of course, if we're going to integrate or take the antiderivative, not only do we have to do the inverse, in other words, divide rather than multiply, and add 1 to the exponent rather than subtract, we have to do it in reverse order for it to be a true inverse. So remember, when we take a derivative, we bring the n out front and multiply it and reduce the exponent by 1. To reverse those steps, we have to add 1 to the exponent and then divide by that new exponent, right? So notice that works right here on f of x equals 2x. If I ask you to integrate here, here's a 1. Let's add 1 to the exponent and divide by the new exponent. The 2's cancel and you get the x squared, and don't forget the plus c, right? So this is really kind of fun and easy to do. And what we will do in class is we will do examples together. So welcome to chapter 4 and our first section, and it'll be fun to work on.